Hey, how's it going? Before we jump into the content, I just want to take a minute to thank you for stopping by the channel and checking out the content. If you like this content and you want to support more content like it, then make sure to subscribe to the channel and like this video. You can also check out the YouTube membership program and cybertrainingpro.com, where I put practice exams and other things that I couldn't put on YouTube. Again, regardless of how you support the channel and my content, I couldn't be more appreciative. Thank you so much, and let's get into the content. Wi-Fi is everywhere today in businesses, in schools, in homes. Literally, it's everywhere. Wi-Fi originally came to be in the late 1990s, but it's dramatically improved over the years into what we use today. Wireless networks use radio frequency or RF waves to allow devices to communicate with each other. Wireless allows for tremendous flexibility and mobility because you aren't restricted by how far that cable can reach. Sometimes the term unbound media is also used when describing wireless networking. Wireless networks are actually very similar to wired networks, except you use RF waves instead of cables, and the protocols that you use for transmitting and accessing data are different too. The standards that wireless networks use today are IEEE 802.11 standards. 802.11 is the standard that defines how wireless devices communicate and how to secure those communications. Wireless hardware performs similar functions as hardware does on wired systems. It uses the OSI layers to encapsulate traffic into frames and so on, with the main difference being that we don't apply chargers to cables. Instead, wireless devices transmit and they receive radio waves. Today, most devices come with Wi-Fi built into the system as a chip on the motherboard, an expansion card that connects to a PCI or a PCI Express port, or a USB device. A lot of these hardware devices might be all you need if you're just trying to connect a few computers together. But what about if you want to make connections into a wired network? For this, you're going to need a wireless access point or a WAP, sometimes also just called an access point or an AP, which allows both the wireless and wired connections to access the same network. WAPs operate at layer 1 of the OSI model, but a lot of WAP manufacturers build in the additional capabilities so that a single box can operate at multiple OSI model layers. All wireless network adapters that you might install need a device driver for the operating system that can talk to the wireless NIC and a configuration utility for everything to work. Today, most of this stuff is nearly always automatic without any additional work by whoever's installing the adapter. Wireless access points are usually configured with a web browser setup process. Now, there's two modes that 802.11 networks operate in and that you need to know about. We have ad hoc mode and infrastructure mode. Ad hoc mode, which is also called peer-to-peer mode, is where systems or nodes communicate directly with one another using a mesh topology instead of having any wireless access points. When two or more wireless nodes communicate, they form an independent basic service set, an IBSS, which is basically like their own wireless network. This is okay for a few computers, but you aren't going to run this on an enterprise. Infrastructure mode uses one or more wireless access points to centrally connect wireless nodes or systems. When you think of infrastructure mode, I want you to think of a star topology that you'd see in wired networks. This mode creates a wireless local area network, a WLAN, and you would also use infrastructure mode if you're connecting wireless systems into a wired network. The area itself that an access point covers in this mode is called the basic service set, or the BSS, and if you wanted to extend that area with more access points, then it's called an extended service set, an ESS, and sometimes it's abbreviated as EBSS. When it comes to wireless range, there's a lot of factors that can impact it. For example, you might have very thick walls in a building that dramatically reduces your wireless signal. Just like when your cell phone doesn't have service, the range can be worse in some areas compared to others. The basic service set identifier, or the BSSID, is a naming scheme for a wireless network that uses the MAC address of the wireless access point. If there's no wireless access point and the nodes are using IBSS, a randomly generated 48-bit string of numbers similar to what a MAC address looks like is going to be used in every frame. Service set identifier, SSID, is the standard name that's applied to the basic service set or the independent basic service set to help the connection form. In basic terms, this is the name that you'd select if you were connecting a device into a wireless network. The SSID is 32 bits long, and it's inserted into every frame that a wireless access point processes. Devices use the same SSID to communicate with each other on a single network. The default for wireless access points is to provide a continuous SSID broadcast so that devices can easily discover that network. If you introduce multiple wireless access points to create an extended service set, or an ESS, then you apply the name to the ESS covering all access points. That way, as devices move around the building, which we also call roaming, they can seamlessly stay connected to all the access points. All of the wireless access points in the ESS connect to a central switch or switches to become part of a single broadcast domain. One of the issues that's unique to wireless communications is that devices can cause interference for other devices. To help minimize this issue, different wireless devices will use specific transmission frequencies. The 802.11 standards are going to use the radio frequencies either 2.4 gigahertz or 5 gigahertz. To begin understanding about wireless transmissions, we need to talk about the transition methods that 802.11 uses. 802.11 defines methods of how devices can communicate using spread spectrum radio waves, which transmits data in small, discrete chunks over the frequency within a certain frequency range. Spread spectrum transmission methods that are defined by 802.11 include direct sequence spread spectrum, DSSS, which sends out different frequencies at the same time, frequency hopping spread spectrum, FHSS, which sends out only one frequency at a time and will shift or hop between frequencies, orthogonal frequency division multiplexing, or OFDM, which is the latest and the greatest, and it's better at dealing with interference, but you won't find it on the earliest 802.11 networks. Wi-Fi networks all communicate on channels, which are a portion of the available wireless spectrum. The 2.4 gigahertz band defines 14 different channels with a channel bandwidth of 20 megahertz each. Some countries limit which channels can be used. For example, in the United States, we only use channels 1 through 11. Something that you have to be aware of is channel overlap. You don't want wireless access points that are next to each other having channels that are close to each other. So for example, if you have channel 4 and channel 5, that might cause issues. Most commonly, you're going to see channels 1, 6, and 11 used because they don't overlap. The 5 and 6 gigahertz bands offer a lot more channels than the 2.4 gigahertz band does. There are around 40 channels available, but countries also limit which of these channels can be used. Fortunately, when these bands are used, the network uses automatic channel switching to prevent issues. If you remember about CSMA, CD, or carrier sense multiple access with collision detection, this helps wired Ethernet networks to allow devices to send data without interfering with each other. Wireless networks have something similar called carrier sense multiple access with collision avoidance, or CSMA-CA. In basic terms, if devices try to use the network and send data at the same time, without these technologies, the data can be corrupted and cause a collision. Wired networks take advantage of full duplex mode on switches, so CSMA-CD is disabled and everything works. Unfortunately, with wireless connections, devices can't detect collisions because radio is a half duplex transmission method, which means that they can't send and receive at the same time. Also, wireless devices can't hear or see other devices that are trying to connect to the same wireless access point to avoid collisions. The 802.11 standard defines two methods for collision avoidance. We have distributed coordination function, or DCF, which specifies rules for sending data onto the network media. If a device detects the network's busy, DCF defines a backoff period to wait, and then it will try again after that period. DCF also requires receiving nodes to send an acknowledge or an ACK for every frame that they process. The ACK also includes a value to tell other wireless nodes to wait a certain amount of time before they try to communicate. Point coordination function, or PCF, is the other method, but currently DCF is the only method that's implemented. Let's go ahead and talk about some of the other important standards that exist when it comes to Wi-Fi networks. You might have even heard of some of these before if you've ever bought a wireless router for your house. 802.11b was the first widely adopted Wi-Fi standard. The throughput is up to 11 megabits per second with a range of up to 300 feet, assuming ideal conditions. 802.11b uses the 2.4 gigahertz standard, which is much more likely to run into interference from other devices. 802.11a is a standard that uses the 5 gigahertz range, which results in less interference from other devices. This also means the standard can run faster with throughput speeds of up to 54 megabits per second. Unfortunately, the limited range of 802.11a also limited its popularity. 802.11g was able to maintain the same speeds as 802.11a with up to 54 megabits per second, except it also expanded the range of up to 300 feet. 802.11g was also compatible with 802.11b because both of them used the 2.4 gigahertz band. This meant that wireless access points could service both standards. If your network only had 802.11g devices, then it would run in native mode, meaning up to 54 megabits per second. If you had 802.11b devices connected, the network ran in something called mixed mode, which only allowed up to 11 megabits per second. 802.11g manufacturers ended up incorporating channel bonding into their devices so that devices could then use two channels for transmission. Unfortunately, because this was done through a proprietary technology from those manufacturers, you needed a network interface card and a wireless access point from the same company for channel bonding to actually work. 802.11n, also called Wi-Fi 4, brought several improvements along with it. This standard requires that all non-handheld devices use multiple antennas for a feature called multiple input, multiple output, or MIMO, to enable devices to make multiple simultaneous connections that are called streams. In general, 802.11 gives excellent speed, but if you increase the amount of antennas up to a maximum of 4, it gets even better. Channel bonding is also available with 802.11n by combining two 20 MHz channels into a single 40 MHz channel. You can see up to a theoretical maximum of 600 megabits per second with 802.11n, but it's wireless, so what you actually get might vary. Fortunately, 802.11n wireless access points use transmit beamforming, which uses multiple antennas to get rid of those dead spots where signal doesn't transmit. 802.11 can support both 802.11b and 802.11g wireless devices by encapsulating 802.11n frames inside of those technologies, which adds some overhead since the faster devices will have to wait for those slower devices to communicate. 802.11n has 3 modes or connection types to transmit data and that you need to know about. Legacy mode means the 802.11 wireless access point sends out separate packets just for legacy devices. Mixed mode, also called high throughput or 802.11-HT or 802.11g-HT, is when the wireless access points send special packets that support the older standards to improve their speeds via 802.11n's increased bandwidth. And greenfield mode is exclusively for wireless networks that only have 802.11n devices. This means the wireless access point only processes 802.11n frames, so there is no backward compatibility included. This standard uses a version of OFDM called quadruple amplitude modulated, or QAM, as a transmitting method. 802.11ac incorporates even more streams than 802.11n by allowing for 80 MHz and 160 MHz channels and higher speeds. 802.11ac only uses 5 MHz band, and it's sometimes called Wi-Fi 5. This standard also includes multi-user MIMO, which gives a wireless access point the capability to transmit to multiple users simultaneously. The standard also uses a version of OFDM called quadruple amplitude modulated, QAM, as a transmitting method. 802.11ax, also called Wi-Fi 6, was released in 2021 to allow improvements in high-density areas. Wi-Fi 6 operates at the 2.4 GHz and the 5 GHz bands, but you also have Wi-Fi 6E, which operates at the 6 GHz band. 802.11ax implements orthogonal frequency division multiple access, or OFDMA. That increases the network throughput and decreases latency dramatically compared to 802.11ac. The Federal Communications Commission, or the FCC, in the United States limits Wi-Fi standard distances to around 300 feet, but 802.11ax performs better as you reach that limit when compared to its predecessors. Here's a quick summary chart of all the 802.11 standards that you need to know about. Interestingly enough, some of these numbers are very difficult to get official sources for. The key things that I would focus on from this chart are the different standards, the bands that they use, and pay attention to the approximate max speed and distance values. A likely question that you might get on an exam could be to compare 2 or 3 of these standards. Have you ever heard of WPS, or Wi-Fi protected setup? Well, as the 802.11 standards started to spread to all kinds of different devices, not all of them were easy to connect to wireless networks or to configure their settings. Wi-Fi protected setup was created to help solve that problem, and it offers 2 different methods. Push button method, which allows you to press a button on one device and then press the WPS button on another device to create an automatically configured encrypted connection. And then we have the pin method to connect a computer to a WPS device like a wireless access point. You do this by pressing the WPS button on your wireless access point, then you locate the SSID of your device, and then you enter an 8-digit PIN as the shared key. This is also called the WPA personal shared key. WPS enabled wireless access points have the PIN printed directly on the device. Unfortunately, WPS is susceptible to attacks, and specifically with WPS PIN numbers, which are short and easy to hack. By default, Wi-Fi has no security enabled. These kinds of devices and connections are made to be easy to configure by their manufacturer. Think about when you last set up a wireless router. You probably took it out of the box, plugged everything in, and turned it on, possibly connecting without even a password. Additionally, wireless signals travel through the air, and they don't require physical access to intercept like a traditional wired network does. Let's talk about some of the security measures that we can use to secure Wi-Fi. Encryption is basically the idea that all the data is scrambled and it can only be reassembled if you have the correct decryption key. WEP, or wired equivalent privacy, is one of the older forms of enabling encryption to secure wireless communications. It uses 64-bit or 128-bit encryption algorithms, but unfortunately, we've learned over time that WEP is relatively easy to crack in just a few minutes, so we don't use it anymore. Wi-Fi protected access, or WPA, or we also call it WEPA, was developed as an intermediate fix to resolve some of the issues that existed with WEP until a full replacement called 802.11i was ready to go. The primary issue that WEP needed to have resolved was it didn't have the ability to authenticate connections. WEP is able to support authentication by using EAP, or Extensible Authentication Protocol. EAP was developed to create a single standard to allow two devices to authenticate with each other. EAP is not a traditional type of protocol, and it acts more like a wrapper for PPP, or the point-to-point protocol, to support many different types of authentication. There's 7 common types that you need to know about. EAP PSK, which stands for Pre-Shared Key, is very common today, and it uses a secret code stored on both the wireless access point and the client system to create a connection using AES encryption. EAP TLS, which is EAP with transport layer security, defines the use of a radius server for mutual authentication, and it requires certificates on both the server and the client. You might even see smart cards used for this type of EAP, which introduces additional administrative challenges. EAP TTLS, or EAP Tunneled TLS, is like EAP TLS, except it can use a single server-side certificate, and it's used in more secure wireless networks. EAP MS Chat version 2, also known as Protected EAP, or PEEP, uses a password function based on MS Chat version 2 and an encrypted TLS tunnel like EAP TLS. This is the most common form of EAP that you might see. EAP MD5 uses MD5 hashes for transferring authentication credentials. This is a weak form of EAP and is used the least out of all the options. LEAP, or Lightweight EAP, is a Cisco proprietary EAP authentication for wireless products. LEAP uses MS Chat authentication between a wireless client and a radius server. EAP Fast, or EAP Flexible Authentication via Secure Tunneling, is Cisco developed and is meant to replace LEAP. Current operating systems support EAP Fast. Due to the popularity of EAP for wireless networks, there was an increasing demand for an equivalent feature for wired networks. Enter 802.1x. 802.1x doesn't use PPP like EAP does, and it puts the EAP information into an Ethernet frame. Simply, 802.1x is a port-based authentication mechanism for a network access control, which means devices that connect have to go through the full authentication, authorization, and accounting process to be granted access to the network or any other system. WEPA Enterprise is a version of WEPA for wireless networks, and it uses 802.1x along with the radius server and EAP for the AAA process, or the authentication, authorization, and accounting process. Unfortunately, the authentication process itself needs some encryption to protect it. That's where TKIP comes into play. Temporal Key Integrity Protocol, or TKIP, is an extra layer of security that WEPA adds to make it more secure than WEP. Specifically, TKIP adds 128-bit encryption using RC4, which is also called TKIP RC4. Unfortunately, TKIP has flaws, and it can quickly be broken almost as quickly as WEP can be. WEPA 2 is the full 802.11i standard that adds needed security. We just talked about TKIP, but one of the key features with WEPA 2 is that CCMP AES replaces TKIP RC4 with a much stronger 128-bit block cipher encryption. Just in case you're wondering, CCMP AES stands for Counter Mode Cipher Block Chaining Message Authentication Code Protocol. One of the things that slowed down the adoption of 802.11i was that not all devices supported AES encryption, but that's changed over time. Keep in mind that you might see WEPA 2 offered with AES and TKIP, but you should always use AES. If you've ever configured a home router, you've probably seen the simplest version of WEPA 2 called WEPA 2 Pre-Shared Key, or PSK, which is also sometimes called WEPA 2 Personal. This is where you just have to enter a key or a passphrase to connect to the network. Longer passwords make this more secure, but the password can still be cracked. A more secure version is called WEPA 2 Enterprise, which uses a radius server to provide authentication services. WEPA 3 is even more secure than WEPA 2 and addresses the weaknesses of WEPA 2 using the Wi-Fi password to encrypt network traffic. WEPA 3 uses simultaneous authentication of equals, or SAE, which generates unique encryption keys between the client and the wireless access point using a key exchange that's based on Diffie-Hellman. This makes it way more difficult for attackers to break the encryption key. There are other security measures that you might hear discussed to increase security that we need to talk about real quick. Disabling SSID broadcast is the idea of hiding the network name from devices, which we also call security through obscurity. Unfortunately, there's a lot of tools out there that can still detect that SSID even if you do this, so basically you end up making it more difficult for users to connect in the end. MAC filtering is when you create a list, also called the whitelist, of allowed systems based on their MAC address. You can also create a blacklist of devices that aren't allowed. Unfortunately, this adds work to maintain these lists, and attackers can just spoof their MAC address after they sniff other wireless devices without even being connected to the network. Isolation or guest network isolation is where you logically separate devices on the wireless network and the wired network. This is commonly used on public Wi-Fi networks. And then geofencing basically restricts access to a physical location. So for example, if you were connected to the network at your desk and then you walked across the street, that signal would drop. Plain and simple, enterprise wireless network equipment is far more feature rich than consumer grade or small home office equipment. There are 5 main ways that enterprise equipment differs. First, we have robust device construction, meaning that enterprise gear is made from higher quality parts, and typically you can add or remove modules or capabilities. Centralized management allows for an administrator to configure many devices in one location. Imagine if you had to log into the administration section for 20 individual wireless access points. That's going to be a job on its own. Vendors like Cisco make a centralized management console, and you can apply configurations to many devices at once. Sometimes you might even use a wireless LAN controller that provides this access. VLAN pooling allows you to divide the wireless LAN into multiple broadcast domains and to use routers to interconnect the domains. Clients can then get assigned to VLANs, which in turn make the network operate more efficiently. Power over Ethernet, or PoE, lets the enterprise gear provide power over the same Ethernet connection that connects the gear to the network. The original standard for PoE is 802.3AF that came out in 2003. When PoE was first released, it supported up to 15.4 watts of DC power per port, but in 2009, it was upgraded to something called 802.3AT, or PoE Plus, and that gives up to 25.5 watts of power per port. Then in 2018, PoE was upgraded again to 802.3BT, also called PoE++ or 4PPoE, with either Type 3 for up to 51 watts per port, or Type 4 with up to 71.3 watts per port. Keep in mind that both the switch and the wireless device need to support PoE for it to work, which makes the gear a little bit more expensive. And the last major benefit of enterprise gear is that personal wireless devices can easily be separated from company-owned gear. Let's discuss the steps that you'll need to take in order to implement a Wi-Fi network. Performing a site survey is the first step to take. This will help you determine any kind of obstacles for your network, and it's going to help you determine the best location for all your wireless access points. The best way to do a site survey involves using a floor plan diagram of the area and to use one of the various site survey software tools that are on the market. These tools make heat maps so you can see a visual of the area. You can identify where interference might exist so that you can use the appropriate hardware like newer technology standards or using multiple wireless access points. Wireless analyzers or Wi-Fi analyzers are devices that look for existing wireless networks in the area to help identify where issues might exist. Configuring client systems is the next step where you need devices that can connect to Wi-Fi networks. Mobile devices like laptops or tablets have the capability built in, but desktops are going to need a wireless card or an adapter installed. The next step is to set up the network, and that involves creating the network to connect to. Some older legacy devices might need an ad hoc network from one of your systems that's enabled in the device settings. More commonly, you'll need to set up the standard infrastructure. This is going to involve configuring wireless access points and physically installing them in the desired locations. Specifically with wireless access points, the type of antenna does matter, believe it or not. Keep in mind that as we cover the antennas, we're going to focus on how the signal is sent out and not necessarily the form factor. First antenna type is omnidirectional antennas or omni antennas, and they radiate signals outward from the wireless access point in all directions. Dipole antennas provide the most function of this type. Typically, you're going to put these in the center of your building to give you the most coverage. Unfortunately, the further you get from the access point, the more the signal is going to suffer or bleed out. You can boost the gain on the signal or use repeaters, but that could cause interference. This type of antenna can also cause glaring dead spots. Unidirectional antennas are directional antennas that send the signal in one direction. Common types include parabolic antennas, like a satellite dish, Yagi antennas, and beam antennas are 2 more types. Patch antennas are flat plate-shaped antennas that generate a half-sphere beam. These are installed on a wall, and they're really good at keeping the signal inside of a room, and they don't transmit the signal out the back of the antenna. Other considerations include polarization, which is basically how the Wi-Fi waves travel, and their path can ultimately impact how good the signal is between antennas. If the antennas aren't properly aligned, you might have a weak signal, and we call this cross-polarization. If the antennas are properly aligned, we call it common or aligned polarization. Antenna placement, as we've mentioned, does matter to eliminate dead spots, give the best signal, and to address security concerns. If you need to extend a wireless network, there are 2 common ways to do this. The first way is to add a wireless access point and use the same ESSID to create an extended service set. This is one of the most common ways. The second is to use wireless bridges to connect 2 wired networks together, or to join wireless and wired networks together. So you've installed a new network, and the first thing that you need to do is verify that everything works. Always, always, always verify. What happens if something doesn't work? We need to start breaking down the problem and figure out exactly what's going on. No connection might mean the equipment isn't connecting to the rest of your network, or that you have incompatible hardware if it's older equipment. Channel overlap can happen with multiple wireless access points or if there's other networks around, because it's not just about your network. If other networks are around and they're using certain channels and you're overlapping with those channels, that can cause interference too. It's important to check for wireless channel utilization to make sure that your devices don't overlap channels. Security type mismatch could mean that either you have the wrong encryption protocol selected or you have an incorrect passphrase, which is more likely. Bad signal and low power levels can happen if you're either too far away from a wireless access point or if there's too many objects that are in the way. The amount of bars that you can see for a connection indicate a metric called Received Signal Strength Indication, or RSSI, but basically that can help indicate this type of issue. If you're looking at the signal strength, the effective radiated power, or the ERP, is the signal strength coming from the antenna, which on non-directional antennas, the signal in any direction will be the same. The effective isotopic radiated power, EIRP, can be used to measure the relative signal strength coming out of a directional antenna to compare the strong end signal with an omnidirectional antenna. You might also want to look at your antenna placement. Slow connection can be caused by several issues, including overworking the access point. Overworked wireless access points can be caused by too many devices or too much traffic like any other network device. This can cause slow bandwidth, jitter, or loss of packets like on a video call where it's choppy, and latency, which is also called lag, again, which is slow connection speeds. We've talked a little about physical issues, but we don't always think about it when we're actually implementing Wi-Fi. Some of the common things that can cause issues include absorption from non-metallic building materials like bricks that can reduce the signal, reflection where metallic materials like pipes will reflect or bounce radio waves instead of sending them in the direction that we want, refraction where, as an example, glass will bend radio waves as they pass through, which causes attenuation, which results in a progressive loss of radio signal strength. These kinds of issues should be uncovered in your site survey so that you can add additional wireless access points, antennas, or adjust their placements so that you can get the best signal possible. Captive portals are basically a website that makes you agree to terms before connecting to a network. You've probably used these at a hotel or a coffee shop before. These can cause slower connections if they aren't set up correctly or if your browser is too restrictive. Radio frequency interference, or RFI, can be a big issue with wireless networks. We've already talked about channel overlaps, but you can get interference from office appliance or all kinds of different devices. I recommend that you use a spectrum analyzer to help detect a lot of these additional signals. It's not uncommon for people to connect to open networks or unprotected networks with default SSID names like Linksys. Unfortunately, these can be created by attackers that can intercept all the information even if it's then sent on to its final destination. Make sure that people don't connect to the wrong SSID, which again could be an attacker. Another thing is, it's not uncommon for firmware updates to cause issues by either making things slow or causing incompatibility issues. Make sure that you test updates first. Another concern is rogue access points, or rogue APs, and these can be a malicious person, but sometimes we'll see employees that buy a home router and they plug it in at their desk to actually give themselves Wi-Fi. These devices aren't managed or secured, which can cause additional issues. And then client disassociation issues are where a client is forced off of a network. There's even an attack called a deauth attack, or a deauthentication attack, that represents an attacker usually trying to crack the connection credentials so that they can log on to the access point.